whenever you see a problem like this, what we're going to do is we're going to draw ourselves a triangle. So you can draw the triangle however you want it to look. I'm just going to draw it like the one I just drew. Right angle. I'm going to call this angle right here theta. You need to mark one of the angles as theta. It doesn't matter which one, except for it can't be the right angle. But I'm just going to draw it like this. So if this is sine and it equals 4 over 5, the top number is my opposite side because sine is opposite over adjacent. And let me back up a little bit. It's really, really, really important that you know what sine, cosine, and tangent are. So there are lots of different things to help you remember sine, cosine, and tangent. Which one did they tell you guys? Did you do SOHCAHTOA? Yes. SOHCAHTOA. Only thing I don't like about SOHCAHTOA, it's not easy to spell. And if you don't spell it right, it doesn't help you anymore. I also have done before some old hippie caught a high tripping on acid. Don't even know if I should be writing that one down, but SOH, sine, opposite hypotenuse, caught a high, C, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. So that's one that you can use. If you're saying that sine is 4 over 5, would the bottom be the hypotenuse? Oh, yeah. Thank you. Losing it today. It's hypotenuse. You can also use I had geometry with my husband with the same teacher and had never heard this. I don't even know where he learned it from. But my husband's favorite one was Oscar has a hairy old arm or whatever other A body part you want to replace that with. But that one doesn't have the S, the C, and the T. So whatever, make sure you got those memorized. This should be hypotenuse. I messed that up. So the opposite side here would be this side right here, which would be 4. And the hypotenuse would be 5. So I'm going to label those. How could I find, so if I want to know cosine, it's moving around there. If I want to know cosine of theta, I need to know adjacent over hypotenuse, which I already have the hypotenuse, it is 5, right? So I've got that. How could I find the adjacent side? Perfect. A squared plus B squared equals C squared here, so A squared plus 4 squared equals 5 squared. You might even remember, does anybody know off the top of their head what it is? It's a 3 right there because 3, 4, and 5 are going to make a right triangle there, but you can also solve that out. So the adjacent side is 3, so cosine would be 3 over 5. Okay. There are, now I bet you did not do this in Math 2 because, gosh, your COVID Math 2 was probably worse than your COVID Math 3 because nobody was doing much good on that first little bit that we were out. Plus, you could only give check marks. There were no grades. And it was not effective. So I doubt you did this. Have you guys heard of secant, cosecant, and cotangent? Yes. Okay, so some of you have, but others probably not. It's okay. It's pretty simple. So we also have secant of theta, cosecant of theta and cotangent of theta. I might should write those words out since they're new. Okay, so secant is secant, cosecant, and cotangent are what we call reciprocal. I guess it is reciprocal identities. What I'm about? No, identities is something different. These are just reciprocal functions, I guess is what we would call them. So tangent is the easiest one. It is the reciprocal of, or cotangent is the reciprocal of tangent. So reciprocal just means the flip, right? So where tangent is opposite over adjacent, cotangent is adjacent over opposite. Now, I was not around whenever they named these. Why secant and cosecant are not reciprocals of each other. I don't know why they named them the way they did. But secant is the reciprocal of cosine. So cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. And then cosecant is the reciprocal of sine, so it's hypotenuse over opposite. So these you can just memorize. They are they're just all the other ones you already knew flipped. So like cosine was adjacent over hypotenuse. Sine was opposite over hypotenuse, and tangent is opposite over adjacent. So, honestly, sine, cosine, and tangent are the ones that are useful. There's got to be a reason secant, cosecant, and cotangent exist and are taught, but they're much less useful. But they still ask about them sometimes. So these will not be a big thing that we are going to do, but they will show up where they ask for them. They're really, you'll see when we do the problems, they're really pretty much the same as doing the problem that we just did. You just are going to have hypotenuse on top instead of on the bottom. So these are just something that you need to have memorized. Eventually, we're not quizzing or testing this week. Secant and one thing I do teach students is that you have to have, like if you're thinking about the reciprocals, you have to have a co in each pair. So you got cosine and secant go together, cosecant and sine go together, cotangent and tangent go together. Like cosecant cannot go with cosine because there would be two cos in that pair. Secant cannot go sine because there would not be any cos if we put those two together. That may or may not happen. So we're going to see problems that look like this. If tangent of theta equals 6, find cotangent of theta. If you do get a problem like this where they're reciprocals, you don't really even have to draw the triangle. You can if you want. But, so like if we draw the triangle, tangent is not a fraction, so how can we make it a fraction? Or 6 is not a fraction, so we make it a fraction by putting it over 1. So this is my opposite and adjacent. So opposite side would be 6, adjacent would be 1. But really, you don't even have to graph or draw that, because cotangent is adjacent over opposite. So you just flip it. So cotangent of theta is going to be 1 over 6. So if you get one like that, you don't even have to draw the triangle. You might also see one like this if, let's do, if secant of theta equals 6/5, find sine of theta. So secant, if we look back up here, was hypotenuse over adjacent. So this is my hypotenuse. This is adjacent. So if I draw a triangle for this one, we're going to have hypotenuse is 6, adjacent here is 5. We know sine excuse me, is going to be opposite over hypotenuse. So we need to find this opposite side right here. We don't have that. We do know the hypotenuse is going to be 6 there on the bottom. So again, we can use Pythagorean Theorem here, so it'd be 5 squared plus b squared, or whatever you want to call it there, equals 6 squared. So 25 plus b squared equals 36. We could subtract that 25. B squared is going to equal 11. We get b equals square root of 11. So that is this opposite side here. So some of these are going to have radicals in them. We'll just get square root of 11 over 6 here. Okay, questions? All right, so we're going to stop here. Okay, questions? All right, there is another kind we're going to see. Example 6. And they look like this. All right, so this time, I don't know the angle. So these are going to be a little bit different in the way that we solve them, but no different really in the way that we set them up. So 5 is the adjacent. 8 is the hypotenuse. So adjacent and hypotenuse is going to be cosine. Cosine of x is going to equal 5 over 8. So this time, it's going to be different because this is not what my angle equals. This is cosine of that angle equals this. So I need to get this x right here by itself, which means I got to get rid of cosine. We cannot divide by cosine. Because, like, if I try that, if I do 5/8, it's going to give me an error. And the reason it's giving me an error is because I have to be doing cosine of something, right? So cosine's an operation. It's not like a variable or something here, or a value. So, like I can divide by cosine of 12, but I can't divide just cosine by itself. I can't divide by x. There is a specific operation that is the opposite of cosine. It's not secant. It's not. No, we're not going to use those, although I like the way your brain is working there. If you look on your calculator, above cosine, what do you see in blue? The inverse cosine. So, like, it is just inverse cosine. So you do cosine inverse of this side, which is going to cancel the cosine, and then cosine inverse of 5/8. So I think you probably should have done that in math too, but might have forgotten it. So cosine inverse of 5/8 is going to be 51.318. And it's just, you just hit the blue button and then that cosine there. So, and that's degrees. So, you may want to put yourself a note. If you are finding an angle, angel. If you're finding an angle, you must use inverse trig. So if you're going to look for an angle, you're either going to do inverse sine, inverse cosine, or inverse tangent, depending on which function you're setting it up with. Okay, so, let's see here. This does have one other thing. I probably should show you this. Okay. Let's do this. So I'm going to teach you special right triangles. I don't know if you learned this or not. Because we don't really have to teach special right triangles. Because they're really just a shortcut. We could just do everything with trig. So there are two types of special rules that are really just shortcut rules. So you don't technically have to know them, but they can come in handy. In fact, I have actually even used these special right triangles in real life. Because there are a couple types of triangles that you see often. One of them is a 45, 45, 90 triangle. So 45, 45, 90 triangle. And so in a 45, 45, 90 triangle, you of course have a 90-degree angle and then your other two angles are both 45 degrees. And so if these two angles are the same, the sides across from them are the same. So like if this is x, then this also would be x over here. So these are going to be, you may also see these called isosceles right triangles. Because they're going to have two sides that are the same, which is an isosceles triangle. That is right, isn't it? Equilaterals, all the sides are the same. Isosceles is two sides. What do you, scaling is what you call it. I couldn't think of what you call it when they're all different. Scaling's when they're all different. Okay. My mind there, I could not think of scaling at all. So I was getting worried that isosceles was wrong, but this is right. Okay. So in this triangle, if you know one of the sides, then the length of the hypotenuse is just x times the square root of 2. So some examples that you'll see for this might look like this. They can mark it different ways. They might just mark that these two sides are the same, and they might tell you this side is 6, and put a question mark over here, put an X or whatever. So if they mark that these two sides are the same, it doesn't tell me that this is a 45, 45, 90, but these two angles have to be equal to each other if that's the case. And since this one's already 90, these two have to be 45 and 45. So if I know one of the sides, to find this missing side right here, I just have to do 6 square root of 2. This is useful like in building because there's lots of times you're working with squares. So there have been times that I have, used this because I'm working with a square and you need that diagonal there. So they can be useful there, a useful shortcut. You also may see some that look like this. They might tell you that this side right here is 8. And then want to know the length of the side. What would you have to do if you know the hypotenuse and you're trying to find the leg? You're going to divide by the square root of 2. Just do the opposite, right? So it's going to be 8 over the square root of 2, which they generally don't like for us to put that square root of 2 in the bottom. So if we multiply by the square root of 2 on top and bottom, we've got 8 square root of 2 over 2, which is 4 root 2. So this is the most, in my opinion, in things I have ran into, most common type of special right triangle that you're going to see. The other type that is fairly common to see is called a 30, 60, 90 triangle. And as you can imagine, that means that one of your angles here is 30 degrees, one is 60 degrees, and the other is 90. These are scalene. All isosceles right triangles are 45, 45, 90 triangles. So if you have an isosceles right triangle, it has to be 45, 45, 90. All scalene triangles are not necessarily 30, 60, 90. So this one, we would not put scalene right triangle because some scalene right triangles are not going to be 30, 60, 90. In fact, lots of them. but it is scaling. So all of our sides here are going to be different. The side you really want to know is the short leg. If you know that short leg, that makes it the easiest to do the rest of the problem. So the hypotenuse is twice the short leg. So if you know the short leg, you can just multiply it by 2 to give you the hypotenuse. And then the longer leg is going to be that short leg times the square root of 3. Again, these are shortcuts. We could set up right triangle, like we could set up trig and just figure this out and get decimals. But these are shortcuts to do. Another reason, I almost decided, I don't really need to show you this, but another reason I wanted to show it to you is they also put a lot of these on the ACT sometimes. I mean, you won't see tons of these problems, but you see them on the ACT, and we all know speed on the ACT is what matters the most. So if you can do this, like, for example, if they give you this triangle here, they tell you this is 60 degrees, and they tell you that this is 4, and they ask for this side right here. If you know the shortcut, you just know x equals 8. And you've just answered this question in no time on the ACT versus having to set up trig and solve it. It's still not that bad to set up trig and solve it, but it's way faster if you use the shortcut rule. So again, you don't have to know how to do it, but it speeds you up some. So like if I had one that looked like this, and let's say that we knew that this side right here was 5. Let's find x and y here. So it's more difficult when you don't have the short leg. If you don't have the short leg, the first thing you want to find is the short leg. So how would I go from the longer leg here? Actually, I should mark this as my 30-degree angle, so we know this is 36 to 90. And then how do I go from the long leg to the short leg here? Divide by, not 2, because that would be if I had the hypotenuse. I would divide by 2. I got to divide by the square root of 3, because the longer leg, it would be multiplied by the square root of 3 if I knew the shorter leg. So I've got to divide by the square root of 3. So x is going to be 5 over the square root of 3, or multiply the square root of 3 on top and bottom, 5 square root of 3 over 3 for this. So this side right here is 5 square root of 3 over 3. Then what would I do to find y? Multiply this by 2. So 2 times 5 root 3 over 3. This fraction is like it's over 1. So that's going to give you 10 square root of 3 over 3. Here. Still a little quicker than setting up trig, not as much quicker. Also, you'll see a question on this worksheet I'm going to give you that sometimes the answer choices are given in 5 root 2 and 6 root 2 and 8 over root 3, 8 root 3 over 3 sort of stuff. So if you don't do it this way, then you have to type all of your answer choices into the calculator to see which one matches. So it's just a little bit, it's a lot quicker to do this right here. All right, questions? Okay, we haven't done any like word problems on this. I'm going to give you guys this worksheet, and hopefully we should be able to maybe get 1 through 4 done before we go. And then if you have time, then try some of these others, but I'm not going to assign it for homework. Okay, so you're going to do as much as you can get done. Hopefully you'll be able to get the first 4 done, and then just read through the others, see if there's any you know how to do without me having to show you. I think